everyone. Today, I'll be explaining a Python program that generates and plots several basic discrete time signals. These are signals defined only at specific time steps, not continuous like analog signals. The program uses NumPy for numerical operations and matplotlib for plotting the signals. By the end, it will show 5 different plots: a unit impulse, unit step, ramp, exponential, and cosine signal. Step 1. Importing the libraries. Here, NumPy is imported as NP. We use NumPy to create sequences and perform mathematical operations easily. Matplotlib.pyplot is important as PLT for plotting. These combinations allow us to visualize mathematical signals quickly. So, NumPy handles the math while Matplotlib handles the visualization. Step 2. Defining the discrete time index. This line creates a sequence of integers from -10 to +10, representing our discrete time index n. Each value of n is like one sample in time. So instead of a continuous time axis, we have separate points, typical for digital or sampled signal. Step 3. Generating the discrete time signals. Let's go through each signal one by one. A. Unit impulse signal. These lines create a signal that is one only at n is equal to 0 and 0 everywhere else. It's also called a Kronecker delta. In signal processing, it's used to represent a single instantaneous pulse. So when we plot it, you will see one spike at n is equal to 0. Unit step signal. This signal is 0 for all negative n and 1 for n greater than or equal to 0. It represents a signal that turns on at n is equal to 0 and stays on afterwards. C. Ramp signal. This one increases linearly. It's 0 before n is equal to 0 and then grows as n increases. It's basically a ramp that starts from 0 and goes up to 10 at the end. D. Exponential sequence. This signal uses an exponential formula. The base is 0.8, so as n increases, 0.8 gets smaller. That's why it's called a decaying exponential. The multiplication by u makes sure the signal only starts at n greater than or equal to 0. In the plot, you'll see it starts at 1 and decay towards 0 as n increases. E. Discrete time cosine signal. Finally, this line creates a cosine wave sampled at discrete points. The argument 0.2 multiplied by pi by n control its frequency. The smaller the multiplier, the slower the oscillation. This signal oscillates between +1 and -1, but only at discrete steps of n. Step 4. Plotting each signal. Now, we move on to plotting the result using stem plots. These lines make the figure large enough, plowed by 10 inches, to fit all 5 plots clearly. Each signal is plotted in its own subplot. Unit impulse. The first subplot shows the impulse signal, a single spike at n is equal to 0. Unit step. The second subplot shows the steps turning from 0 to 1 at n is equal to 0. Ramp. The third subplot displays a linearly increasing sequence for positive n. Exponential. Here, we see the exponential decaying from 1 down to near 0. Cosine. And the last subplot shows the discrete time cosine, an oscillating pattern with evenly spaced points. Final layout. Type _layout open and close parentheses adjust the spacing so labels don't overlap. Finally, PLT.show open and close parentheses displays all 5 discrete time plots in one figure. So to summarize, we generate 5 standard discrete time signal using NumPy. We plotted each using stem, which is perfect for discrete data. The output shows a spike for the impulse, a constant line for the step, a rising slope for the ramp, a decaying pattern for the exponential, and a wave-like pattern for the cosine.
These signals are fundamental in digital signal processing, where we analyze or process signals in discrete steps instead of a continuous time.